Hey, this is Horner, and we're going to look at 7.6. This is using Newton's second law for rotation. It's your reading guide. We've got a square plate, and the square plate has a nail stuck into it, and maybe it's stuck to the wall, but it's not so tight that you can't rotate. So you can actually rotate this whole thing around the axle. So we give it several forces. One of them we push right from the axle. One we kind of push off the edge here. Here we've tied a string and we're pulling it this way. We've tied a string here and pulling it this way. So in a lot of these cases, we think that it's going to rotate about the axle and it should kind of go in this direction. So this is counterclockwise, so we would say that it has a positive rotation. They want us to rank in order from largest to smallest the angular accelerations of alpha 1 through alpha 4. So alpha, remember, is the angular acceleration. So let's go ahead and first determine how are we going to think about angular acceleration since we're only given force. Well, remember our new equation for torque is really equal to the moment of inertia times the angular acceleration. And for each one of these, we can really just go back and rearrange this for angular acceleration. So angular acceleration is torque divided by the moment of inertia. Because we have four forces acting on the same object, our moment of inertia is the same. So we're really going to just say that the angular acceleration is proportional to the torque. So the one with the biggest torque, the force that provides the biggest torque, will also provide the biggest angular acceleration. So let's look at each one of these. The first thing we're going to do in red is go ahead and let's make our lines of action. So remember, the line of action will go straight through the actual the force itself. Now this one I'm going to make a little bit longer because remember, we want them to try to come down and be perpendicular to the axle itself. So we're able to do these, and the next thing we need to do is start a moment arm and go to each one of the lines. Well, this one is parallel, so there's really no moment arm for F1. In fact, for F2, even though it's way up here, we still can't go this way because that's still parallel. By perpendicular, we see that this line going from the axle out to the line of action for F3 actually give us a line, and then we'll do a different color here for the line of action for F4. Now that we have all these lines of action, we notice that there is no moment arm for F1 or F2. So because of that, torque 1 is equal to torque 2, and those are both 0. And it's because, like we said, there's no moment arm for either F1 or F2. There is for F3, and there is one for F4. So these two have the smallest, should have 0 angular acceleration. So we're going to just put angular acceleration of 1, which is equal to angular acceleration of 2. So that would be the smallest because it is 0. If we look, the next biggest one will be the torque on number 3, and it's because it has this little moment arm here. So that's torque number 3, which means angular acceleration number 3. And then the one with the biggest angular acceleration will be the one that has the largest torque, which is 4. So the angular acceleration here is 4. And that's how we rank these. So we really looked at the torque, knowing that the moment of inertia for this rectangular piece, or square piece, I guess, is the same for each one of the forces. Let's go ahead and take a look at the next part, which is number 30. Here we've got a solid cylinder, and we have a cylinder that is not solid. It has most of its mass concentrated on the outside. The mass here is concentrated throughout. They both turn on a frictionless horizontal axis, or axle. And so this axle is going into the page, so is this one. There's a rope tied around each one with a block, and on 3 we let them both drop. So 1, 2, 3, drop, and we notice that one of them hits the ground first. We need to know which block hits the ground first. It is not going to be a tie, and then we can explain it. So the biggest part here is not the answer, so we'll do the answer very last. Remember, they're going to grade you on your physics. We know that the weight of the block, so the weight of the block will provide the acceleration. So the weight of the block will make both of these accelerate, and that acceleration also then provides a torque on the cylinders. So what we need to do is look at the cylinder, so the cylinder with the smallest rotational inertia, remember that's I, will accelerate, will have a higher acceleration. So if you look up the moment of inertia for a shell, that would be equal to mr squared. And then the one with the solid, this one is equal to 1/2 mr squared. So the solid actually has a smaller moment of inertia than this one does. And because of that, we know that block number 1 will accelerate faster. So it's easier to get this thing turning than it is to get this one turning. And that is the answer to number 30. Remember, the solution is the thing that's really important, not necessarily just the answer itself. For the next one, we have a metal bar, and this metal bar is kind of unique because what they've done is they've put an axle through it, and on the ends here, they've actually put some compressed air on the inside, and then that compressed air is comes out on the ends. So the compressed air goes in through the axle, so there's some sort of tank that's pushing that in, and then the air is shot out the sides. And when it does that, then this thing actually rotates, and it rotates in this direction because we know that the air is being pushed out, so it's got to be able to rotate in a counterclockwise or positive direction. On the figure, they want us to draw vectors to show the forces exerted on the bar. Then label the moment arms for each one of the forces. So for this one, we've got a force, and we'll call this F1 right here. We know that the moment arm will be our radius, and so this is R1. Then we've got a force going this way on the second one and a radius of R2 on the second one here. So now we're making this bar really start to rotate pretty quickly. So that's the first thing we do. Recognize what we're trying to do. It says, what force does each escaping jet of air exert on the bar? So that's what we're looking for. We know that F1 should be equal to F2, and so we're going to say that that's the overall force. And radius 1 is also equal to radius 2, so we're going to say the radius is R, and so that makes it a little bit easier to see. At this point, we're going to, it says the forces in your drawing exerted torque about the axle. So write an expression for each torque and then add them to get the net torque. The expression should be in terms of the F and the known quantities such as M and L and G. Notice that the bar has a mass M and a length L. We have to be careful because our radius is not going to be R in this problem, it's going to be L over 2. So this problem does look very similar to an AP Physics 1 problem. Our first expression, we know that the torque for number 1 is going to be equal to the torque for number 2, and that's because we're just multiplying our radius times our force. Now we have to be careful because we've got to have everything in the right unit and the right labels here, and they told us it has to be an M, has to be an L, and then we also need to make sure that we can have it in F. So F, M, L, G, any other known quantities. So our net torque here should be equal to, we have 2 of these things going around, so that's 2 times R times F. And do notice that the net torque is positive because it is going in a counterclockwise fashion. The only problem that we have with this answer is it does not, you'll notice there's no R here, but we do have something that would be 2 times R, and 2 times R is the length of the whole thing, and that's one of the things that they told us we could use. So we're going to just say that this is L times F. Next one says, what is the moment of inertia of this bar about the axle? And the only thing you can do here is look it up, and that would be 1/12 of m times L squared. So that makes it pretty easy. For the next part, it says, according to Newton's second law, the torque causes the bar to undergo an angular acceleration. We have to use the results from B and C to help us write an expression for the angular expression, and then they want us to simplify the best we can. Remember, the angular acceleration from the last problem we did is equal to the net torque divided by our moment of inertia. So now we're just going to plug everything in. Remember, we said that our net torque is L times F, and our moment of inertia then would be 1 over 12 times ml squared. At this point, we can cross off 1L, get rid of the squared, and we're left now with the expression of 12 times F. Now, how do we get that? Notice that this is 1 over 1/12, so we're going to multiply both the top and the bottom by 12. So if I multiply this by 12, that goes away, and then I have 12 on the top, so that's 12F over m times L. And that would be our solution to number 31 all the way through letter D. Let's go ahead and take a look at letter E. And for letter E, it says you can now use rotational kinematics to write an expression for the bar's angular velocity. So at this point, we're going to say the angular velocity, remember our fishy, is equal to, you spend a lot of time when you are fishing. And so if we want to, we now need to figure out the bar's angular velocity, the equation for that. So this is the change in the angular velocity, which is equal to the final angular velocity minus our original angular velocity, and we know that this is 0. And that's actually equal to alpha times the change in time. So all I did here is I solved this equation for the change in angular velocity, and that's just alpha times the change in time, which is what we have here. From above, we know that alpha we said was 12 times the force over m times L, and that was what we had up here, so it was 12F over ml, so we just took this and moved it here. And then we also have the change in time, so there we go. Now we are set. Finally, solve your equation in part E. So we're looking now for force. So at this point, we're just going to say the force is equal to, we've got the mass, so we have the mass times L times omega, and now we're going to put that over our 12 times the change in time. So all we did here was we solved this equation. Okay, we solved this equation for our, because we know that it was this, we solved it for F. So when we do that, we multiply both sides by ml, which is what we did. So that's ml times omega over 12 times delta t, because the 12 and the delta t have to go on the bottom, and this is our final expression. So now we can use this with experimental measurements. We could determine the force of the exerted gas, and that is the end of 7.6.